And then we'll be seeing the training methodology and the intake. And then I'll start with the ASIC flow, the main technical part of it. And then we'll see the physical design flow. What are the steps? What is physical design all about? And then I'll take you people to the placement process that how happens at our institute. So this is the agenda for today's demo. And a short instruction to everyone: if you have any queries at any point of time, you can just stop me at that point, and please feel free to post your questions. Cool. So saying that, so we are the one of the prime institute in the advanced VLSI studies, and we are located very next to Bagmane WTC in the Bengaluru. And all our faculties and trainers are with minimum 15 plus years of experience. And Takshila provides a 100% placements to all its students. Speaking about unique features of Takshila, we follow industry standard curriculum, and every student that take up the course will get a 24/7 VPN access. That is whatever the tool part will be there. Naveen, you're saying audio is not audible. Yeah, Naveen, I informed you to connect to audio. You are only connected via video. So please turn on your mic, get connected via audio so that my voice will be audible for you. Okay, okay. So yeah, as I was saying, every student will get his own tool access. That is, all the logins and credentials will be sent to the student so that you can access your tool, you can access your logins whenever you want, so that you can get connected and get whatever experience you want. You can explore your tool how much you want. Moving on, speaking about semiconductor companies. So semiconductor companies, we can just broadly categorize them into three different sectors. One is product-based companies, then is service-based companies, and then we have EDA companies. So EDA companies are those that provide us EDA tools to follow all our VLSI activities. So Cadence, Mentor Graphics, Synopsys. So these are the three prominent companies that provide us their EDA tools so that we can perform all our activities, all our VLSI activities. And speaking about product-based companies, we all are aware of many product-based companies, like it can be Intel, Qualcomm, Samsung, Nvidia, AMD. All these companies' products, we are aware that in our cell phones we see their processors. In other, modern electronic gadgets, we see all the products of these companies. So these are the basic product-based companies. Speaking about again service-based companies. So first of all, service-based companies are those that provide services to these product-based companies. So whatever the manufacturing or whatever the development that takes place in product-based companies, there will be a part that will be handled by the service-based companies. So we have Wipro, Infosys, Aricent, Synapse, Sankalp Semiconductor, Graphene, and many more service-based companies in the India. So yeah, that's about a short note about semiconductor industries. Moving on, the eligibility criteria to get into the physical design job is the either your BTech or MTech passed out, a 60% of minimum is expected. You can be from EEE background or ECE or ENTC, anything is fine. All right, guys, I hope I'm clear till eligibility criteria. And moving on to the physical design core job opportunities. So as I already mentioned earlier, if you take up the physical design course, you can get job roles like a physical design engineer, you can become STA engineer, you can become DFT engineer, physical verification engineer, EMIR sign-off engineer, and methodology and flow engineer. So what is this STA, DFT? We'll come to that, don't worry, but these are all the job roles that any physical design engineer would get. And speaking about the salary scope, if you are any fresher with any of the VLSI course completed, you will be getting 4 to 5 lakh of package. And as your experience grows, as your knowledge grows, our package will also vary. Like you are 2 to 3+ person, then you'll get a package around varying 6 to 10 lakh. And you are 4 to 6 plus person, they'll offer you the position of a team lead. And if you become more experienced on that and more knowledgeable person, then you'll also become a project manager in the respective company. So even your packages will vary according to that. So yeah, that's about the salary scope. Okay, before getting into the course overview, anyone have any queries what I addressed till now? No doubts, right? Okay, cool. So physical design course overview is something what all topics you'll get to learn inside this course. So the very first thing is it's basics of Unix and Linux. That is, as we operate all our EDA tools in the Unix or Linux environment, having basic knowledge of how to operate your files, how to open the files, how to change the directories, all that minimum basic command knowledge is required. So that will be taught. After that, we'll be having brush up sessions. That is all the BTech basics, what we learned, starting from your MOSFETs, diodes, what are semiconductors, and then the digital part, all the basics, your K-maps, what are combinational circuits, what are sequential circuits, and then CMOS circuits. All those basics brush up sessions will be taken up. Once all the basics are done, then we will have the ASIC flow introduction. That is, even in today's demo, I'll just introduce you people to the ASIC flow. But when you take up the course, you will get to learn in detail what is this ASIC, what each step has to do, how it is done, everything you'll get to learn. So once your ASIC flow is done, then we have introduction to Verilog. That is Verilog coding language. So you don't need to get expertise in Verilog coding language, but having a basic knowledge of in what all styles of this language are there, how code is written, how to analyze the code, having that much of knowledge is very much required for any PD engineer. So that will be introduced to you people. So once that is done, then we have a topic called DFT. So DFT stands for Design for Testability. In when I take up the ASIC flow, I'll explain you people what is this DFT. But yes, you'll get to learn about that. What is it, how it is done, what is that process exactly? All those things we will get to learn. So once DFT is done, the next topic is the synthesis. Again, in the flow, I'll explain you. But what is synthesis? How to perform it? What is the role of a PD engineer in that particular process? All those things you'll get to learn in detail. And then we have a topic called STA. So STA stands for Static Timing Analysis, which is a quite big topic. So we have divided it into 2 sections. So you'll get to learn lots of terminologies, lots of new things in this topic. So you'll again get to learn in detail about STA. So once that is done, then your actual physical design starts. That is the actual theoretical part of physical design. What is it? How it is done? What all steps are there? What is your role in it? What all challenges a PD engineer made to encounter? All those things you'll get to learn. And then followed by physical design, we have physical design verification. That is what all designing part you do in the physical design that needs to undergo certain checks to ensure that the job of the physical design engineer is proper. So once all this theoretical part is done, all the students will be offered 2 projects to the students. Both are on 28 nanometer technology. So one will be completely guided by your trainer or lab technician, whoever you will be having. The second project will be more for the student exploration. There also you will be having your trainers and mentors to guide you, but that will be more for a student exploration, right? So this is all what you will learn in the course overview or in the duration of your course. So the duration of this course is 5 months. Every day you will be having 1 hour of theoretical classes followed by the lab sessions when you get into actual PD part. And if you take up the weekend batches, so for every weekend there will be 6 hours of class, same theoretical class followed by the lab sessions. And maximum intake per batch is only limited to 15 to 30 students. And as I already mentioned, all the students will get the lab access when your tool that is when your practical session starts, right? Okay, so now I'll start the actual ASIC flow. Before that, if you have any queries, I'll just address them and I'll start with the ASIC flow. Yeah, anyone have any queries?
No.
No queries. Okay, what about others?
No, ma'am.
No queries. Okay, cool. So now we'll see what exactly this ASIC flow is. So if anyone wants to manufacture a chip or wants to manufacture a process, all the way where it starts is from the customer. So if I am the customer and I want to manufacture any particular process for any particular functionality, I'll be knowing the things like what should be the functionality of my processor, very first thing, and what power I want to operate it, and at what frequency I want my processor to work. So all these are basic inputs the customer will be knowing. So all these inputs we call it as specifications. So any customer who wants to get this processor ready, he will come to the architecture team with all these inputs as specifications. Clear? So what architecture team will do? The architecture team will design or just build a blueprint depending upon the inputs, whatever that has been given by customer. So he will decide what should be the size of your that particular processor, what all blocks he may need to involve in that, what all components he may need to add to achieve that particular functionality, to achieve that frequency, and to make that particular processor to work at that power. So he will plan all those things and he will decide the final cost of that processor to design it, and what might be the time duration that particular processor may take to get ready. So once all his calculation is done, he will go back to the customer and he will discuss that. If customer agrees for that cost and for that duration of time, then the actual process starts. Okay, so once the customer agrees, the first step is to write the code, that is the RTL design. So RTL stands for register transfer level, nothing but just your Verilog code language. So what these RTL people will do, they will write the Verilog code for the functionality of that processor. Whatever might be the that processor job has to be done. So that functionality will be written in code form by the RTL people. That is in the Verilog language, they will write the code. So once this code is written, then that will be verified by the RTL verification people. So they'll just ensure that for whatever functionality that code is defining, whether it is achieving or not. That is the job of the RTL people. So till here, till RTL verification, what all steps comes, we call it as the front end part. All the remaining steps, what you're saying in the flow, that we call it as back end. Okay, so any doubts in front end part? Anyone have any queries?
No, ma'am.
No, right? Cool. So now let's see what all steps that we require in the backend. So once the code is ready, the next step is to do the or take that code and start the next step. The thing is that whatever EDA tools we use, they cannot understand this code. When I say code, how it will be just like in a simple English. Even if you people are aware of your VHDL language, you will just define the name of that particular function. You will give inputs, outputs, and you will just write the functionality. Like for example, if I want a full adder, what we will write, you will just write that it will be the XOR of the inputs. That is A XOR B XOR C or something like that. But the EDA tools cannot understand those standard English letters. So what has to be done is that English language has to be converted to a circuit level or gate level connectivity. That is done by your synthesis tool. So what exactly synthesis is? It is a process that converts this Verilog code, whatever RTL people have written, that to a gate level netlist. So when I say gate level netlist, as you're seeing in this image, it will be just like what are inputs, outputs. These inputs, what are they driving? Are there some logic gates? Are there some combinational circuits or sequential circuits? And output of those circuits where it is driving. So pure circuit level connectivity, it will convert. That is the job or role of the synthesis. So once this is done, next comes a process called DFT. So as I already mentioned, DFT stands for design for testability. So what is this design for testability is? So once your chip is completely manufactured, before delivering it to the customer, we want to ensure that the chip is working fine. To ensure that, at DFT stage, we insert a certain piece of logic so that once your chip is manufactured, you can apply some test vectors or input vectors to that particular chip and ensure the functionality of your chip. Right? So to use that logic at very later stage, when your chip is completely manufactured, we are inserting that piece of logic or that piece of code at the very earlier stage. One more thing, so whatever this logic you are inserting, that can only tell us whether chip is working fine or not. In case if there is any error, in case if there is any bug in your chip, there is no way that we can go back and get it fixed. If it is working fine, package it and deliver to your customer. If it is any error in that, just go back and put it in the dustbin. So that's how the job of a physical design engineer is critical. I think you all are aware that if a chip has to get manufactured, there will be millions and millions of dollars or rupees that will be invested in it. So we have to very sure that whatever chip we manufacture, that has to work. So though see, once your chip is designed, before going to foundry, before getting manufactured, it goes so many checks. But still, it's very unsure that there may come a chance that your chip at final stage after manufacture may not work. So to ensure that functionality at the very final stage, we insert the logic at the stage called DFT. So the DFT stands for design for testability. Right? I hope all are clear till DFT. So after DFT, what all steps you are seeing, that's the actual physical design steps. So from what is this floor plan you are seeing, all the remaining steps what you are seeing till routing. So these are all the steps of the actual physical design engineer job. So once your complete physical designing is done, next step is sign off. Sign off is nothing but physical design verification. So as I said, whatever design we do, that has to undergo certain checks. So once it passes all the checks, that will go to foundry and your chip will get physically manufactured, and it next process is packaging and testing. So once it passes the tests, all the tests, the chip will be ready to send to the manufacturer. So this is how any chip or any process will go through all these steps. Right. So now we will see what exactly happens inside the physical design. So now, before getting into physical design process, first we need to understand what are the input files we require to perform the physical design. So very first input is the gate level netlist. So what is this gate level netlist? The same file that we get as output from the synthesis team. And what is this synthesis? I told that whatever the code you have written in the Verilog form, that will be converted to a gate level or circuit level connectivity. So the same file which defines the functionality of our overall chip or overall processor is the very first input file we require. The second file which we require is constraints file. We call it as .sdc file. This is a file that contains certain constraints, or I can say certain restrictions, like how many clocks your design have, at what clock frequency they operate, what should be the input delay for those clocks, what should be the output delay, what's the maximum fan out your design can have, what is the maximum transition your design can have, and many such constraints are there that we dump in this file or that we write in this file. Right? So basically you want to design that particular processor and you want it to work it within these constraints, within these restrictions. We want to ensure that we are able to achieve the final functionality of our processor. Right? So the next input file are the two libraries. That is whatever cells we require. I said, right, When you convert it to the circuit level connectivity, it may be some basic logic gates, it may be some combinational circuits, it might be some sequential circuits. So all these what are circuits gates are there, their information we require. So all that will be present in these two libraries. So one is logic library, that is .lib. So this file contains all the delay information and the power information of all your standard cells. So when I say delay information, if you take up any particular cell, like if you just take up your OR gate or any logic gate, what is the amount of time it requires, what is the delay that particular cell have. Similarly, for all the cells you will be using inside your design, this particular logic library will contain its delay information and power information. So what is power information? What is the leakage power of that particular cell? What is the internal power of this particular cell? All those details will be present. The next file, input file we have is physical library, that is .left. So as name itself signifies, it contains all the physical details. So physical details like what is the size of your cell, or in what shape it is, in which direction you can use it, and what are the layers that are present for that particular cell, and what are the rules or you may need to maintain if you use that cell. All those physical related information will be present in the physical library, that is .left. So these are all the very basic and mandatory inputs that we require to perform the physical design. And one more input file we have, that is .upf file, which is very optional, only in case when we have a multi-voltage domain design. In that case, we will be using this .upf file. Yes, the above four inputs are very much mandatory. Right? Any doubts in this? All are clear with input files?
Yes, ma'am.
Okay, cool. So now we will see what exactly physical design is all about. Okay, so the very first step in the physical designing is the floor planning step. So floor planning is very much similar to, I always take up the example of if you are building your house, what we will do first, we will go to an engineer and we will get a blueprint ready. And what will be there in a blueprint, we decide that where should the main door come, where should your living area come. So basically what you are doing, out of the available area, you are making or you are deciding how your house should be. So the floor planning step is very much similar to that. So first thing in floor planning is we have to decide what will be the height and width of our block. So whatever the figure you are seeing on your left side, so first step is to decide the size of this block, that is what should be the height and what will be the width of it. So that we call it as aspect ratio, that is what is the height and what is the width of it. So once you decide the size of your block, the next step is to decide the position of your IO ports. So what are IO ports? IO ports are those that communicate with external world. So if you consider a full chip, there might be multiple blocks inside it. There might be 2 blocks, there might be 10 blocks. So if you are designing a single block, the IO ports of this block might be communicating with other blocks. Or if you're designing a full chip, your IO ports may communicate with the external world. So it is just similar to the thing that if you take example of your cell phone, we have a separate port for to charge your cell phone. You have a separate port to insert your audio jack. So just similar to that, even our chip or processor have the ports. So we will decide where the ports has to come, whether it should be on the left side, whether it should be on your right, top side or bottom side. We will decide what is the position of our IO ports. So once IO port positioning is done, the next step is to decide the position of these tiny colored blocks what you are seeing. So basically these blocks are called macros. Oh, sorry. So these are called as macros. So what are these macros are? They are just ready memory blocks that are ready to use inside your design. Okay, so we have to decide depending upon their what where you have to keep. So this is the whole of your area, so where you have to keep the particular blocks. And how we decide that? Depending upon where or for what purpose that particular macro is. So if I consider this particular macro, where is it communicating, whether it is communicating with the neighboring block or whether it is communicating with certain IO port. So depending upon its connectivity, we will decide the position of these macros. And the position of these macros is very much important because this is what decides our further steps. If we make a efficient floor plan or an optimal floor plan, then your further steps will become easier. Right? So as I was saying, if you take up your full chip, so these are the blocks or these are the IO ports that communicate with the external world. So I was saying that we have to plan our IO ports. So IO ports, many times it will be scenarios. Usually, if you are designing a block, from top end, you will get the instructions where to place your IO ports, depending upon to which block they are communicating. Like you can see, these particular two blocks are communicating. So they ensure that the IO ports will be on these two ends so that you can directly connect them when you insert them in a full chip. So depending upon that, your top end person will give you the file, or sometimes it will be in your hand to decide the position of these IO ports. Right? And next important thing is, whatever this outside part of your block is there, that we call it as die area, and the inner part where we saw those all those macros were sitting, that particular area we call it as core area. And all these blue colored lines, what you are saying, that is basically the space between your die area and core area. That part we call it as the, or that is the space where your IO ports will come and sit. Clear? So if I have to go back, so just a second. So this is your die area outer side. This inner area is your core area. And all these tiny colored lines, what you are seeing, these are the IO pits between your die area and the core area. So once floor planning is done, next step is the power planning. So what happens in power planning is, we have to ensure that throughout your block, or where all your components will come and sit, we have to ensure that all should get sufficient amount of power. So for that, what we'll do, we draw vertical and horizontal power lines, that is your VDD lines and VSS lines. So it will be just in form like a grid. So a power grid we will put to ensure that all components that come sit inside your core area can tap power from its nearby grid. So why we are putting this power grid? So out of your IO ports, only at one point you'll be having a power port. For example, if I take, so this is the power port where I am feeding. So from here I'll insert the power. Even the block which is sitting very far away from the IO, that is far away from the power port, should also get sufficient power. Then only my final functionality of whatever my chip is designed to, that I can get. So using these horizontal and vertical power lines, we are ensuring that we are providing sufficient power supply all over the chip or all over your block. Right? So that's about floor planning and power planning. So once floor planning and power planning is done, the next step is placement. So what is placement is, in floor planning, what we did, we only made these ready memory blocks or macros to sit inside the core area. Still, depending upon your functionality, there will be so much of other standard cells that has to still come and get accompanied inside the core area. So when I say standard cell, the standard cell can be a basic logic gates. It can be any complex combinational cell. It can be any your SRAMs, DRAMs, or it can be any basic sequential cells, right? So all these tiny walls like structure, what you are seeing, they are basically the standard cells. So in placement stage, what will happen? We are telling the EDA tool that all those standard cells should come and sit inside this core area. So here, what is the challenge is, we have to ensure that all these cells have sufficient place to sit. No cells are overlapping on one another, and there should not be any congestion. That is, all cells should have sufficient space so that they can sit. So all those things we have to take care in the placement. What about partitioning? Okay. So partitioning is, I think you saw in the first image, right? Okay. So what is partitioning is, if you are designing a full chip, as I said, you will be having multiple blocks, right? So all the physical design process you have to perform on each and every single block. So at partitioning stage, what they will do is they will divide this whole chip, like either your TL or manager, what he will do, he will divide this full chip and he will assign each block to a team or to a person. That depends upon your team strength. So for example, if one person is handling each one block, he will assign to a PD person and he will tells that perform PD on these blocks. Once the whole physical design process is applied on all the blocks, he will bring all the blocks and he will combine them and insert them inside a full chip. So that is what partitioning all about. Clear? So moving on, we were in the, okay, good. So we were in the placement stage. So in placement, what happened? All the standard cells came and sat inside the placement area or inside the core area. So what is the next step? I decided in floor planning what I did. I decided the size. I inserted all the IO ports. I made sufficient a proper position for macros. Then we made the power planning. Then we allowed all the components, that is all your standard cell, to come and sit inside the core area. So in the next step is the clock tree synthesis. So what is clock tree synthesis? If you have any sequential cells in your design, we know that we have to provide them clock so that they can function. So again, similar to your power, there will be clock port at one point of your block or chip. So we have to ensure that all the sequential elements that have widely spread all over the core area has to get clock at the right time. So only when your sequential cells get clock, then only they can function, or then only they can read the data. So depending upon the your sequential cell arrangement, we will build a clock tree in a way that all the sequential cells, which might be very near to your clock port or which might be very far away from your clock port, get clocks at the same time. So there are many structures, many patterns we follow depending upon the requirement. We ensure that clock is reached to all the sequential elements. At that particular step, we call it as clock tree synthesis. So once clock is also provided, what is the last remaining step? That is routing. Routing means just providing connectivity between all your sequential elements, macros, and the IO ports. So now in placement, what we did, we just brought all the standard cells and we have just made them sit next to each other depending upon the functionality. Only when I provide, depending upon what is present in your .p file, if I make connection between these standard cells, then only my chip can work, right? So using the metals, all these colored lines, what you are seeing, these are all different metals. So using these metals, we will make the connection between these standard cells, macros, and the IO ports. That is what routing stage is all about. Clear? So once this routing is done, we have to ensure that no metal piece have been shorted. There is no open metal wire that is freely dangling. And there are certain rules that you need to follow. That is, what should be the spacing between two metal wires, and how long, what should be the length, maximum length of a metal wire. Depending upon what design you are doing, there will be certain rules that you need to follow. So depending upon that, we will ensure that the whatever routing solution we have done, that is the optimal one. So this is the last step in our physical design process. Okay, guys, you have any queries in any of the steps?
Yeah, ma'am, I have a question for you.
Yeah, please go ahead.
Ma'am, is macro also part of Netlist, or macro is a different thing from Netlist?
Macro is also a part of Netlist, but it is like, instead of how can I say, if you want a half adder, instead of you start from scratch, that is, you'll start from your logic gates and build a half adder, and you already have a ready half adder in your library. So what we'll do, the better optimal solution is to just take that readily built half adder and continue with your design. That's what just the job of your macro is.
So pre-placed cell, like just
Sorry, I didn't get.
macro is just like a pre-placed.
Yeah, we can say like pre-placed, but it is readily available. You are the one who will place that macros.
Okay, ma'am.
Yeah,
Thank you, ma'am.
cool. So any other queries? Others, no queries in any of the steps? Okay. So before moving to the verification part, I'll take you people to the tool part. So how exactly all these steps or all these designs look inside the tool, where a design is loaded, so that it will be more easier for you people to get connected to the tool. Right? I hope you people are able to see the screen, right? Yeah. Is screen visible to all?
Yes, ma'am.
Okay, great. So this is how the design would look like at the very first stage. So here I have only loaded all the input files which we discussed. So all those netlist libraries and all those files I have just loaded. So this is what your block is. So this is the die area and inside is the core area, right? And if I just zoom in, so as I said, so this is the space between your die area and core area where you will put all your IO ports. And all these tiny blocks at your origin, these are your macros. As this is very initial stage, we have not made placement for these macros, so they are just sitting at the origin of your block. And all these colored lines you are seeing, these are your actual standard cells. So if I just zoom in, so these are your standard cells. So as I said, your standard cells can be any logic gate. So here we have NAND, NOR, here we have OAI cell. So it can be anything depending upon your functionality. Clear? So this is the very first stage. When you load all your input files, this is what we get to see. So let's see what happens when floor planning is done. So here floor planning is done. All the blocks have are there in their positions. So depending upon what group they belong to, you can see there are different colored blocks. So why there are different colors? Depending upon whatever groups or whatever hierarchy they belong to, they have just shown with different colors. And these are the power lines, what I said. So horizontal and vertical power lines. So here you can see VDD and VSS lines, right? So this is the floor plan stage. Again, as placement is not done, your placement, that is your standard cell, are still outside your block area, right? So this is how it would look when floor planning and power planning is done. So after floor planning and power planning, what is the next step? So the next step is the placement. So this is how placement is done. So now you can see that all the standard cells that were lying outside are now dumped inside your core area. So if I just zoom in, you can see all your standard cells, right? So depending upon the functionality they have, they will be placed inside the core area, right? So this is how it would look when placements are done. So once placement is done, what is the next step? Next step is to provide clock to the sequential cells. That is the clock tree synthesis stage. So here, this is the clock tree synthesis stage. And here you can see that clock trees are built. So these are the clock trees. So depending upon wherever you have sequential cells, there will be clock trees built. See, here it is. Clear? So once a clock tree is also built, the last stage is the routing stage. Yes. So if I just zoom in here, you will see all the same colored metal wires, what you saw in the presentation, right? So we have horizontal wires, we have vertical wires, and wires. So basically connection is done between the standard cells, your macros, and the IO ports. So this is how we have to design. Yes, able to get an idea how it works. Any queries?
Hello.
Yes.
Apart from that, I have a question. Before placing the standard cell like gate and netlist, is it necessary to place the macros first into the core?
Yes, good question. Why it is necessary to first macros is whatever this placement you will do, we have to ensure that that placement is optimal, because whatever what I can say, whatever space you have available, if you don't make optimal solution for your macros, for example, if you put any macros inside in the center somewhere, then whatever these standard cells will come and sit, they don't have optimal area to sit. In that time, what will happen? There will be a congestion. We say there will be a local hotspot. So whatever this placement we are doing, even after the placement, we have to ensure that there should be sufficient space so that routing can take place. Like for example, we'll assume that this is your core area and you just made all your standard cells to, have just abutting them. You are just dumping very next to each other, just something like this. Okay, just try to imagine if this is the case in routing stage. If I want to make connection, this particular cell might be communicating with some other cell, and this cell might be communicating with some other cell. If I don't have sufficient space in between these standard cells, I cannot make the connection possible, right? There it will be a mess. So having a right positions for these macro is very much important. Actually, while designing, many a times it happens, right? Like whatever macro positions we might have done, that might not be optimal. So we go to placement stage, we make the placement, and there we'll check that whether we have that sufficient space or not. That is what we call it as congestion. We ensure that our placement stage should be congestion free. If there is any such congestion, we come back to the floor plan stage and we check that if we can make any alter or any changes to the position of macros so that your placement can get better.
Okay, thank you. The
Okay.
macro size bigger than standard cell. Size
My
of this macro size.
I didn't get okay, wait, I didn't get your question. Can you come again?
Hello.
Yeah, please.
So macro size is bigger than the size of the standard cell.
Yes. See, macro is one complete block. It's like you assume your macro as a full header and assume one single AND gate or NAND gate. Obviously,
Okay.
your macro will be bigger in circuited because it is like collection of gates or collection of circuit.
That's why we have to place first on the core.
Yes.
Okay. Thank you, ma'am.
Okay. So others, any other queries in any of the stages? No queries, no doubts. Okay, then I'll take you people back to the presentation. So once all this routing and your designing is done, the next step is the sign off, or what we call as physical design verification. Here our design has to go through various checks. Like we have DRC check, that is the design rule check. So as I already mentioned, there are certain rules like spacing rules and other rules we have to maintain. So we have to ensure that our design is free of all these violations. And then we have certain electrical related rules. I'm sorry. So we have to ensure that there is no IR drop, and we have to ensure that there is no antenna related issues and many other issues also we have to verify. So once your design passes all these verification checks, then your design will be ready to go to the foundry and get manufactured. Right? That's a very top level overview about physical design process or physical design course. So speaking about placement process, so when you join, you'll take up the course and your sessions will start. Parallelly, your resumes will be created. And when we get requirements from the client companies, your resumes will be sent to the client companies. And when your resumes get selected, you have to go through the interview rounds. So usually there'll be like 2 to 3 set of interview rounds, and all your trainers and institute people will support you with all your interview rounds. So when you get shortlisted, there will be small sessions of like just like soft skill program, just to ensure that you get prepared for how to answer in your interviews, how to interact in your GDs and all those things. So once all your interviews rounds are done, once the results are out, and if you get selected, until your onboarding takes place, institute will be there at your back for your support. So that's about the placement process. And these are all the list of companies that our institute have tied up with. So we'll be getting requirements from these many companies. So depending upon requirement, when our students are ready, we'll just send their resumes and start with the interview process. And moving on, so these are the list of students who recently got placed in these respective companies. And if any of you are interested to know which student got, by taking up which course they got into which company and all those things details, then it's actually updated in your website, so you can just go and take a look at it. So, and this is the infrastructure, how our theoretical sessions and lab sessions would look like. And yeah, so that's all from my side. If you have any queries or any questions, I'll address them.
Can you tell me about the fee payments?
That you have to check with the management. I am not aware of it. I think you might be having a number of HR or something. You can just call to that number and check out the details.
Yeah.
Yep. Any other queries?
No, ma'am.
Yes.
The company will also take the written exam before taking an interview.
I didn't get your question.
Hello?
Yeah. Please, can you repeat your question?
Yes, ma'am. The company will take the written exam before taking an interview.
I don't think so, but yeah, once please check with the management. The joining process and all, I'm not much aware of it. You can check with the management people.
Okay, thank you, ma'am.
Okay, someone have a query. How can I do practical online? Okay, so as I already said, the VPN access and the tool login access will be given to you. Just if you have a laptop and an internet connection, you can log into your tool at any time you want, and you can work on your tool. Okay, cool. So yeah, any other queries? Okay, in future, if you have any queries, any doubts, please feel to contact this number, and we are also our email ID, so you can just post your query to the respective email IDs and get it clarified.
Thank you so much.
Okay, guys.